This video, I'm going to prove an even stronger lemma compared to the one in my last video. It says that if H is a non-empty finite subset of G and it's closed under multiplication, then H is a subgroup of G. Once again, that symbol means, at least in group theory, it means is a subgroup of. In the last lemma, we weren't given that H is a finite subset, and we were able to show that H is a subgroup of G if H is closed and it had inverses. Well, they're telling us that it's closed. So in this proof, we can say, based on my last video, all we need to show is that H has inverses. Okay. Now, the only real difference between the statement of this lemma and the last lemma, in fact, let's look at the last lemma. It says that a non-empty subset of H, non-empty subset of H of the group G is a subgroup if and only if A and B is in H implies AB is in H, that's closure, and if for every A in H, A inverse also lives in H. Well, we have the closure. So all we have to do is show the inverses. And if you like watching proofs like this, you should seriously subscribe to my channel, because this is what we do here. We prove lemmas and theorems and consequences, do proofs by induction. Whatever you like, you'll find on my YouTube channel. Okay, so like I said, we have to show inverses for each element A in the group. Well, let's pick an element H in a group. But first, let's argue that there is an element H in the group. Since H is not the empty set, it's non-empty, that implies that there exists an A in not G, but in H. It's also in G, because H is the subgroup of, is a subset of G. Okay, now it's a finite subset of G. So what we do is we consider, we consider S equaling to A squared, A cubed forever. Now, since H is closed, all of these elements are in H. A is in H. Say A times A is in H. That's A squared. That's in H. Multiply it by A again. That's in H. That's A cubed. A cube's in H. Multiply it by A. It's closed. That's A to the fourth. It's in H. If you keep multiplying by A, it's still in the group. Okay, so now this set H is a subset of H. Now, since the order of H is finite, the order means the number of elements in H is finite. That implies, since this looks like an infinite number of elements in S, that implies that S has duplication. Duplications. Suppose A to the R is equal to A to the S, where R and S are natural numbers and say R is less than S. Now remember, this is going on in G. Since G has the cancellation laws, A to the R minus S is equal to E. On both sides, I killed off A to the S. But, that's in S, which is a subset of H. This is in H. Okay. Most importantly, that's in H. Then, A times A to the R minus S minus 1, which is A to the R minus S, which is E. But so since I'm multiplying this by something and I'm getting E, that implies A inverse is in H. Because both of these are in H. Let's state that. Where both A and A to the R minus S minus 1 are in H. So we show that A inverse is in H, and that is all we had to show. We had to show that H has inverses. And let's see where it was. Somewhere A was arbitrary. For any A in H, we can do this same thing all over again. For each and every element in H, this argument holds. A inverse is in H. Okay. Therefore, H is a subgroup of G. Theorem has been proven. If you're into watching mathematical proofs like this, subscribe to my channel. Please leave a comment. Click the like button. That really helps out. See you folks in the next video. Always remember, keep watching and learning. Have a great day.